Let's draw a picture of this problem. We have a disk that's rolling on a level surface. Here's the disk. I'm going to put a little mark on here where it's touching the surface of the ground at that particular moment, and there's a force that's coming from a wind that's blowing on it like this. So that's causing this to roll and accelerate, and as it rolls a little bit further, I'll draw it a little bit later, and sure enough, as that rolls around, this little dot ends up being at this particular location. So this distance that it travels here, which I'll call delta S, is equal to this distance on the surface of that disk. Those are one and the same, because this is presumably rolling without slipping. So this gives us the ability to connect this rotation of this disk with its linear velocity. So in particular, the angle that it has rotated, this angle right here, delta theta, is equal to delta S, the distance that it's traveled linearly, divided by the radius of that disk. Now, by proportional reasoning, we also know that if we were to take delta theta and divide it by delta t, we would get the angular velocity of this, which is delta S over delta t times that r in the denominator, which is its linear velocity divided by r. And similarly, by the same sort of proportional reasoning, we can find that the angular acceleration is equal to the linear acceleration divided by r. These are important relationships here that will help us figure this out. Let's now address this question of why is it we can't find its acceleration by just taking 2 newtons and setting that equal to ma? The reason is there's a sneaky other force in here. This other force is a force of friction that keeps this thing in contact with the board here. So here's the force of the wind, and this way is the force of the friction, and they're going in opposite directions. The force of the wind is applied uniformly over this, so it doesn't apply any torque, but this force of friction is applied just at that surface at a distance of r from the center, so that does apply a torque. Now we have all the equations that we need to solve this thing. So let's write those out. Okay, let's say the force of the wind minus the force of friction is equal to ma. That's the linear part. And then we also know that the torque is equal to I alpha. This is the angular part. This we can clean up a little bit by using the fact that the torque is equal to the force of friction times the distance at which it's applied, which is r. And the moment of inertia is mr squared over 2. That was given to us. And the angular acceleration is equal to the linear acceleration divided by r. That's what we found just over here. So now we can clean this up a little bit by getting rid of this 2 as it cancels one of the r's, and the r on this side cancels the other part over there. If that confused you, make sure to go through and look at sections that have to do with algebraic solutions of simple formulas. But this leaves us now with this result that the force of friction is equal to ma over 2. And notice that the radius has disappeared completely. All we need to do now is solve these two equations simultaneously, and perhaps the easiest way to do that is to simply add this equation to this equation here, and you'll see the two forces of friction disappear. So I find that the force of the wind is equal to ma times 1.5, or 3/2. So if I solve for the acceleration, I just find that the acceleration is the force of the wind, that is that 2 newtons, divided by the mass, which is 0.5 kilograms, times this factor here inverted, 2/3, which is equal to 8/3 meters per second squared.